Hello dear students, my name is Junaid and I am your physics tutor for NEET, and today we are going to discuss an important topic in electrostatics, that is the torque on, let me put the heading also, the torque on a electric dipole, torque on an electric dipole placed inside a uniform electric field. Place it inside a uniform electric field. Let us discuss this case. Let me draw the uniform electric field. By uniform electric field, we mean that the value of the electric field, the magnitude of the electric field, and the direction of the electric field is going to be same throughout the space. Is going to be same throughout the space. Here, this is a uniform electric field E, and I will place a dipole. Suppose dipole AB I have placed inside this uniform electric field. Now, we know that what is an electric dipole? Electric dipole is an arrangement of two equal and opposite charges. Suppose this is an electric dipole AB, which means that there are two charges and they are separated by some distance. This distance we take conventionally as 2a, and this arrangement gives us the dipole, and it is dipole moment. The physical quantity is defined as 2a, the length of the dipole, multiplied by the charge of one of the poles. That is, magnitude of either of one of the charges multiplied by the length of dipole gives us the physical quantity, that is the electric dipole, which gives us the strength of this electric dipole. So this is an arrangement of electric dipole placed inside a uniform electric field E. Suppose this is the center of dipole O, which means this OB equal to A, also OA equal to A. This is the center of dipole, this is the center of mass of the dipole. O is the center of mass of the dipole, and this distance is A, this distance is also A. Let initially this dipole is at an angle theta with respect to this electric field. Now, we know that for a charge inside an electric field, the force experienced by the charge is equal to QE. So, this is a plus Q charge here, this is minus Q charge here, which means that for a positive charge, this force is in the direction of electric field. This is the force in the direction of electric field QE, and similarly, this is going to be the force on the charge minus Q in a direction opposite to the electric field experienced by this minus Q charge. This force is experienced by this plus Q charge, this force is experienced by this minus Q charge. Therefore, the net force on this arrangement, on this dipole inside a uniform electric field, is going to be 0. Why? Because the plus Q charge will experience a force plus QE, and the minus Q charge will experience a force minus QE. The net force is going to be 0. The net force on this dipole in a uniform electric field is going to be 0. Now, our actual work is to calculate the torque on this electric dipole. So what is a torque? Torque is actually the turning effect of these forces. These two forces will try to rotate this electric dipole will try to rotate this electric dipole about its center of mass O. So we have to calculate that turning moment. We have to calculate that moment of force. For that, let us calculate first the turning effect of this force QE. For that, it will try to rotate this dipole about this axis passing through the center of mass. So we know that torque tau is force into perpendicular distance from the center of rotation or center of mass. So let us calculate this perpendicular distance. This point is M, therefore this BM is the perpendicular distance, which means that if this is the torque tau 1, it is going to be force is QE and the perpendicular distance is BM. I can calculate from this right triangle, if this is theta, initially the dipole is at an angle theta with respect to electric field, so this angle is also going to be theta. So this will give me tau 1 is equal to QE into, from this right triangle, sine theta is equal to perpendicular by hypotenuse, which gives me this perpendicular length as A sine theta. This is A sine theta. Similarly, the turning effect of this force, is going to be tau 2, and that is again the force QE multiplied by the perpendicular distance, that is going to be AN, and AN is again from this right triangle equal to A sine of theta. Now, what is the direction of the torque? Both the forces, both the torque tau 1 and tau 2 are going to rotate this dipole clockwise. These two torques will try to rotate the dipole in the clockwise direction, so the net torque is going to add up. So the net torque will be tau is equal to tau 1 plus tau 2, and that is going to be, adding these two, 2A sine theta into QE will be the net torque on this electric dipole AB in this uniform electric field. Now we know that this dipole moment is P equal to the distance or the length of dipole multiplied by the magnitude of either of the charges. So I can write this tau equal to 2A into Q, I can write as P, and then I have electric field E and then sine theta. This is the expression for the torque on an electric dipole placed inside a uniform electric field. Now, since this torque is a vector quantity, P is also vector quantity, E is also vector quantity, which means that torque is also a vector quantity, and I can write this tau equal to P cross E in vector notation. Why P cross E? Because when I go from, this is my P vector and this is the E vector, this is angle theta between these two, the going from P to E gives me the direction of this, that is the clockwise direction of the net torque. So this is the resultant torque in vector notation. Now let us discuss the important or the cases for this torque when it is going to be maximum. Tau will be equal to tau max when sine theta is equal to 1. In this expression, when sine theta equal to 1, because sine theta equal to 1 is the maximum value of sine theta. So sine theta will be 1 at theta equal to pi by 2, which means that the torque will be maximum. This is the uniform electric field when dipole is at angle of pi by 2 with respect to the electric field. Then there will be maximum torque on this electric dipole, and that maximum torque is equal to P. That maximum torque is equal to PE when the dipole is at pi by 2 with respect to the electric field. When will be this torque minimum? The torque will be minimum when theta equal to or sine theta equal to 0. In that case, tau will be tau minimum, and that is going to be 0. Minimum torque will be 0 on this electric dipole when it is parallel or anti-parallel to the electric field. This gives me theta equal to 0 or pi. That is when, if it is an electric field, if the dipole is either parallel to the electric field, in that case the torque will be minimum, that is 0, or if it is anti-parallel, minus q plus q, anti-parallel to the electric field, in that case again the torque is going to be 0. And these two cases of minimum torque, that is 0 torque, are the cases for stable and unstable equilibrium. The torque, first case, when theta is equal to 0, tau is equal to 0, this is a case of stable equilibrium. This is a case of stable equilibrium, because when the dipole is parallel, this side is plus q charge, this side is minus q charge. When this is parallel to this electric field at 0 degree, if I try to give it a small angular displacement by theta, the net torque will again, because that is clockwise, we have seen that will bring it back to the direction of electric field. So this case is a case of stable equilibrium. However, when the dipole is anti-parallel to the electric field, this side is plus q charge, this side is minus q charge, the torque is 0 again on this electric dipole. However, if I give it a small angular displacement, the net torque is clockwise, that will rotate it and bring it parallel to the electric field. And therefore this case, theta equal to pi, is a case of unstable equilibrium. Is a case of unstable equilibrium. Let me summarize what we have done. We have placed an electric dipole inside a uniform electric field, and we have seen that there are two equal and opposite forces acting on the two charges, plus q and minus q, and the net force is 0. However, the two forces are not along the same line of action. They have a different line of action. Therefore, the turning effect of these two forces tries to rotate clockwise in our case, and the clockwise rotation of this dipole results in a net torque on the electric dipole, and that net torque is equal to PE sine theta, where P is the electric dipole moment, that is P is equal to Q into the length of dipole, and this gives us the scalar form of the net torque on this electric dipole. in the vector form, the tau in vector notation is equal to P cross E. This gives us the vector notation for this torque on the electric dipole. And then we have seen the two cases. First, the case of maximum torque. The maximum torque occurs when theta is equal to pi by 2. That is, the dipole is perpendicular to the electric field. In that case, the torque is maximum, that is Pe, and the torque is minimum when when dipole is parallel or anti-parallel to the electric field. And in that case, we have again two cases, one of the stable equilibrium, one of the unstable equilibrium. And theta equal to 0 is a case of stable equilibrium, and theta equal to 0 is a case of unstable equilibrium. Thank you.